Thank you so much for the introduction. My name is Umar, and I'm going to talk about our research on detecting advertising and tracking request chains. I'm a postdoc at the University of Washington, and this is a joint work with collaborators from the University of Iowa, University of California, Davis, and DuckDuckGo. In this talk, my objective is to convey three main things. First of all, I want to show that advertisers and trackers abuse request chains to track people, and they recently have been found to use them to bypass privacy protections against cross-site tracking. Secondly, I want to demonstrate that existing countermeasures are not equipped to protect against privacy harms caused by request chains. And third, I want to explain our novel machine learning-based approach called Khaleesi, which is purpose-built to protect against advertising and tracking request chains. Now, before I explain our technique, I want to very briefly explain what we actually mean by request chains. So in a typical HTTP request, the browser sends a request to fetch a resource from a server. The server evaluates the request and returns the requested resource if it is available. And in cases where server cannot fulfill that request, but it knows that another server can, it redirects the browser to fetch that resource from the other server. Then browser will have to issue a subsequent request to get the response. So overall, these requests and responses between the browser and different server form a sequence of requests and responses. And this is what we refer to as request chains in this paper. These request chains are of immense importance to advertisers and trackers because they allow them to share tracking information across origins. Trackers cannot do that inside the browser because they are restricted by a security mechanism called the same origin policy. So as a workaround against that policy, trackers rely on request chains. The technique here is actually fairly simple. It first involves reading the accessible data directly from the browser and then embedding that into a redirect, which will force the browser to send that to the intended entity, for example, tracker and advertiser here. More recently, we have seen that trackers are now relying on request chains to bypass third-party cookie restrictions that are put in place to protect against cross-site tracking. The basic idea behind these protections is to only allow cookies from domains that have been visited by the user as full-fledged websites. And since most people do not intentionally visit tracking websites, trackers lose access to their cookies. But trackers have found a way to bypass this restriction as well. And their technique is to rely on request chains to trick the browser into actually visiting the tracker's website. And they typically achieve this by rewriting the links on the website so that when people click on different links, they are navigated to advertising and tracking websites before they can land on the intended web page. And as a result of this bouncing, these websites, which are visited as full-fledged websites, are able to seed their cookies, which they can later access as third parties. So now that we have looked at some of the ways in which advertisers and trackers can abuse request chains, let's see if existing solutions are effective at protecting against these threats. So most people rely on ad and tracker blockers to protect their privacy on the internet, but unfortunately, these tools are not equipped to effectively block request chains. And the reason I say that is because they operate at the level of individual requests and try to block known trackers instead of the tracking behavior based on some block list. So for example, to block this request chain, despite that chain showing an obvious tracking behavior early on, these ad blockers will only be able to block it at the very last hop. People have improved these ad and tracker blockers with the help of heuristics, where the general idea is to learn on tracking behavior instead of trackers. And these heuristics are essentially a narrow set of rules, which very specifically define a particular tracking behavior. And it makes them excellent at detecting those behaviors. But as you can imagine, that heuristics would fail in unfamiliar and unseen conditions. To demonstrate that, let's look at two request chains here. One is for cookie syncing, and the other is for bounce tracking. And this heuristic that we have on the left side will only be able to block the cookie syncing request chain. And it will be clueless against this bounce tracking request chain. These heuristics have also been improved with the help of machine learning, where the idea is to generalize on a broad range of tracking behavior so that you can detect them very easily. And the state-of-the-art approaches, like the one presented in the session earlier, try to organize the website execution in form of graphs and use the execution traces of trackers to detect them. And these approaches perform excellent in terms of detecting generic tracking behavior, but they're not very effective at detecting specialized tracking behavior, like the one carried out through request chains or fingerprinting, for example. Their main limitation is that they do not utilize the necessary context to effectively detect request chains. For example, to detect this cookie syncing request chain, these approaches will operate on individual requests in isolation and will not use any information learned about the chain so far. So overall, we can conclude that prior approaches are not purpose-built to detect advertising and tracking request chains, which causes them to have accuracy issues. To bridge that gap, we propose Khaleesi, which is a specially designed approach to detect advertising and tracking request chains. Our key idea is to capitalize on the sequential nature of the request chains because the purpose of request chains becomes apparent as they grow larger and larger. And I will try to motivate that insight with an example. So if you look at this request here, we are in a position to make an inference. For example, we know that this request is to a third party, and it is trying to exfiltrate some information, which could be an indication of tracking. And when we receive its response, we can see that it was not just reading information, but it is also sending that to another third party, which affirms our initial inference. And as we let the chain grow, we can see that it is a bilateral data exchange between an advertiser and a tracker, which is a clear indication of tracking. So overall, by analyzing the request chains in a sequential manner, we are in a better position to capitalize on a much richer and necessary context to effectively detect request chains. We used that sequential context to develop a machine learning-based approach called Khaleesi, which can detect advertising and tracking request chains. Khaleesi first uses the web extension APIs to capture HTTP requests and responses at the network and the JavaScript layer, and arranges those requests and responses in form of chains. Once Khaleesi has organized those request and response pairs into chains, it extracts features from the request, response, and sequential properties, and labels them with popular ad and tracker blocking filter lists like easy list and easy privacy. And after labeling, Khaleesi feeds these chains to a machine learning classifier, which learns to detect advertising and tracking request chains based on the request, response, and sequence properties. In Khaleesi, we capture request chains that are initiated at the network and the JavaScript layer. At the network layer, we simply link the subsequent request and response pairs that appear in HTTP redirects. And at the JavaScript layer, we try to capture two kinds of request chains. First are the top-level navigations that are typically initiated with window.location API. And the second are the requests initiated from a same script that share common identifiers. And overall, by capturing these chains at the network and the JavaScript layer, we capture a broad range of tracking behaviors that are executed with request chains. And examples include cookie syncing, bounce tracking, and several other techniques. So after we organize these chains, we extract request, response, and sequential features. With request features, our intention is to capture properties that can tell us what the request might do. For example, by capturing the URL length, we can identify the scenarios where trackers are trying to exfiltrate data by embedding it in the URLs. So if there are a lot of identifiers embedded in the URL would be longer. With response features, our intention is to capture properties that can tell us what the response will do if we let it execute. In that case, the length of the response, for example, can indicate if a tracking pixel is loaded. With sequence features, our intention is to capture properties that can tell us what the request chains has been doing. So if we encounter a lot of unique domains in the chain, it might be an indication that cookies or other tracking information is exfiltrated to multiple advertisers and trackers. So using those features, we train a random forest machine learning ensemble, and we use EasyList and Easy Privacy as our ground truth. And our test data is the request chains on the Alexa top 10,000 websites. So after we train the model, we test it on various crawling configurations and also using tenfold cross-validation. So that number here, 98%, is for the tenfold cross-validation. But most importantly, we are able to detect more than 1,250 new advertising and tracking domains that have not been yet blocked by EasyList and Easy Privacy, which almost all ad and tracker blockers use. So overall, in conclusion, I first demonstrated that advertisers and trackers rely on request chains to track people and bypass privacy protections. Then I showed that existing solutions are ineffective at detecting request chains. And after that, I showed that Khaleesi bridges that void by leveraging sequential nature of the request chains to effectively detect them. We have a lot of additional analysis, which I did not get a chance to talk about here. Some of that includes Khaleesi's evaluation on 5 different data sets, where we interact with different crawling configurations, which include different browsers and interaction. Khaleesi's robustness against commercial and other classifiers that are proposed in research, and also about its runtime performance. So I would encourage you to read the paper to know more about that. Lastly, I want to mention that we package Khaleesi as a browser extension, and you can visit the link in the URL to try it out. Thank you so much.